Now we will study about the cluster analysis. To start with, we will have the basic concepts that are associated with the cluster analysis. So now let's try to understand what is cluster analysis. In simplest terms, what it means is that given a set of data points or a given set of objects, we'll group them in such a way that similar ones go together. So as you can see here in a three-dimensional data, so there are points which are located in the space, and what we can notice is that they seem to belong to three groups. And when we do a clustering, all we want to do is to make sure that within a cluster, whatever objects or points are there, the distance between them is small, and also that the distance between the clusters or the inter-cluster distance is maximum. So that indicates the distinctness of one group from the other group. And where can we use such a analysis? It is used in for example, in marketing, because so many times the marketing team would like to understand the customer base and divide them in some form so that they can do a target marketing. So this is to say, it will be far more efficient if you are targeting a subset which is likely to buy your product rather than the entire universe. So similarly, you may do it with the land use. For example, you may take the soil characteristics of, let's say, the land, by and large, the entire land in our country. So then you may be choosing 1,000,000 points. And when you are looking at the soil characteristics in the form of the fertility or the minerals within the nutrients, or there can be several chemical parameters that can be used for indicating the soil characteristics. So you may be, there will be a million data points, but the point is, if the government wants to understand these characteristics of the soil and thereby create a policy, it is very unlikely that though the 1,000,000 points will have some amount of difference between them, they would like to create a set of 1,000,000 policies. Most likely they want to club the soil, the land which is similar together. So then you are possibly getting about 10 or 12 types of the land based on the soil characteristic. But you will be able to do the similar characterization using several other things based on the land uses. For example, is it a forest land or a urban land, or is it a river, or is it so? There can be several ways in which you can analyze and group. And similarly, it is used in the other businesses. For example, the insurance, when an insurance company is selling a policy holder a premium. So they want to know, whenever they want to sell a policy, they want to know how much premium to charge from the customer, because typically it depends on some of the characteristics, because they think that some customers are more risk prone than the other. So in that situation, they again want to group them, because they cannot have a 1,000 groups or 1,000,000 groups, because even if they have 1,000,000 customers. So they want to characterize or group them in a way so that, or they may even think in terms of a new product based on the grouping that they had done. It is possible that out of the 1,000,000 customers that they have, for 100,000 customers, it is a good idea to create a new product which is going to be most effective. So similarly, there may be situations when you want to divide a city into based on the various characteristics or attributes, or you may want to study the seismology, or you want to study the earthquake-prone zones. As we know, there is always a seismic activity within the earth, and then we also have numerous earthquakes, many of them very small. So they may be harmless, but the point is that we may be having a data of millions of earthquakes that happened. And if we study what is the epicenter for these earthquakes, then we may be able to understand the fault lines on the earth. So the cluster analysis can be used in numerous contexts and for numerous purposes. And let's also understand what is not cluster analysis. Cluster analysis is an unsupervised form of machine learning. And here you are not going to tell what is the target of what you want to find out. So in case of a classification, we have seen it was a supervised learning, and we had class labels and we were learning from the training data. And cluster analysis is also not a simple segmentation. So if you have a group of students and you divide them into sections or divide them into groups for an assignment, it is not a cluster analysis. And it is also not a cluster analysis if you have done a query based on some requirements. So let's say a car manufacturer has many customers, million customers in the country, and just wanted to understand them, and then you wanted to look at how many of them belong to a particular profession. So how many of them are teachers. And so here the query objectives are very clear. So even if you are grouping the customers into say teachers or lawyers or accountants, we are not doing a cluster analysis here. And how do we determine the quality of the clustering that we have done? So one simple and very generic characterization is that it should have high intra-class similarity and low inter-class similarity. So that is to say, between the clusters, the distance should be high, and within the cluster, they should all be close. So this is a desirable characteristics, but given the kind of applications where we work on, we cannot visualize the differences everywhere. That is to say, it is when we are plotting the points along on a two-dimensional plane, we have a very clear concept of distance. So in that sense, we can find out which are the points which are close and which are the points which are far off. But the cluster analysis is seldom done on two-dimensional geometric space. So most of the time we have very diverse types of attributes. For example, we are looking at a customer. If we want to group them or segment them, we may be using one is age, one can be the income, one can be the profession, one can be the location where they live. And as we can see, these attributes are of so distinct types or different kinds, we cannot think in terms of plotting them along coordinates and measuring the distances. So in fact, the cluster analysis is more effective based on some intrinsic purpose for which we are doing it. And it is good if the data analyst is able to find some hidden patterns. That is, so many times we apply cluster analysis when we have a large number of data points. So if it is 50 or 100, possibly we can observe and determine. But if it's a million data points, we may want to look for patterns. And if the data analyst or the data scientist found a pattern which was never imagined, then they may be happy with the cluster analysis. And how do we measure the quality of clustering? It is typically using a similarity or a dissimilarity matrix, which is done using the distance between two objects. And the distance function itself is very difficult to define, considering the wide nature of attributes. Some of them are interval scaled, some of them are Boolean, categorical, etc. And all the attributes are also not equally important. For example, a mobile phone company, they want to understand their customers, and somehow they got also an attribute of their customers, let's say, which is the height of the customer. So it's not going to be, it's very difficult to see how you can correlate this attribute. They may be having other attributes, which is the address, which is the age, So here they need to be clear what is the value that they want to assign it. So it is possible that the income is more important than the address. So this kind of the understanding, semantic knowledge of the data is required before you can do effective clustering. And we expect a cluster analysis algorithm to offer scalability, because we want to deal with larger and larger data sets, be able to handle attributes of different types, and should be able to create clusters with arbitrary shape. And many of the clustering algorithms have a tendency to find the clusters which are circular or of specific shapes, rather than finding the ones with the arbitrary shapes. And it should also be something which should work without too much of domain knowledge. And so many times we are operating in an uncertain environment, and there we want to create some patterns which will help us gain some knowledge. And expecting a domain knowledge may be a constraint there. And when we have the data, and we can easily expect the noise and outliers for various reasons, and the data quality cannot be expected to be of very high. And also many times the algorithms take the data in a particular sequence and process in a particular sequence. It's important that the algorithm is not sensitive to the order of records. And many times the data that we deal with has large number of attributes, and so the algorithm should accommodate high dimensionality of the data. And if there are any user specified constraints, it's good if the algorithms can take it. And finally, whatever results that they give, if there is an interpretability or the usability associated with it, then the clustering will be useful. And let's look at briefly the types of data that we deal with. So broadly we deal with the interval scaled or binary or nominal, ordinal or ratio variables or variables of mixed types. So if we look at interval scaled, so it is simply we can find a mean, and we may be able to normalize the data using a z-score, which is essentially difference of the point from the mean and standardized using the standard deviation. So thereby we are reducing the variation of the data, and thereby for example, we may be getting the income which is in the range of 0 to billion, and A is in the range of 0 to 100. So if we can do some standardization, we may be able to use both of them together for analysis. Then we can use the similarity and dissimilarity using the various distance measures that we have. The most popular one is the Minkowski distance, where we can use any exponent and thereby determine. And if we use the q is equal to 1 in this case, where the power to which we are rising the distance, then what we are getting is a Manhattan distance. And if we are using 2, we are getting the Euclidean distance. And the distance we arrive using the Minkowski properties, they will be following these properties which are required for a distance. But many times we may require a weighted distance. So in such case, we may look for more complex distance measures. And we can have a binary variable. There can be 2 objects with a large number of binary variables. For example, there are 2 patients in a medical database, and we are looking at 100 symptoms for yes or no. So in such cases, we may take a different approach. We may create a contingency table to look the distance between 2 objects, where we are finding out where they have same value. For example, both of them are true or both of them are false, and then where they're different. So the distance measure, if the true and false have a symmetric weightage, so they are equally important, then the distance measure can be done using the b plus c by a plus b plus c plus d. Or if they are asymmetric, then where 0 is less important than 1, we may want to ignore d and then we can get the same formula. And the Jaccard coefficient works when there is a asymmetric binary variable where 1 is more important than 0. And in that case, the similarity will be A by A plus B plus C. And we may have nominal variables, which is a more generalization from the binary variable. For example, it's a profession. So it may be a teacher, lawyer, accountant, so on. So in such cases, you may consider based on the number of matches. So if the matches are m among the total number of variables, which is p, we may use this distance measure as p minus n by p, or we may be able to do the similar thing using a large number of binary variable to represent each value, whether teacher or not, whether an accountant or not, so on. So in that case, we can use the previous approach. And some of these variables can be ordinal. In that sense, it's like a nominal variable, but there is a order is important. For example, we have a rank. So if for example, a student's grade in a subject A, B, C, D, E, A and B are closer than A and C. So in such case, we will have to use a rank. So we may be able to find out the Z-score in this case by using the rank of the object minus 1 divided by the maximum value for the rank minus 1. So thereby we are getting a value within the range of 0 to 1. And now let's look at the cluster concepts. It's important to note that the meaning of cluster itself can be ambiguous in the sense that we can change the parameters and can get a different set of clusters. So we had earlier the data of this form, and we somehow decided that we want to create 2 clusters. Then we are likely to get, most of the algorithms will give us this type of clustering, because clearly we can see a high proximity among these and among these. And let's say we wanted to do 6 clusters, then we are going to get different set of clusters. And if we want to go for 4 clusters, we are going to get a different set of clusters. And this again is going to be slightly different based on the type of approach or the algorithm that we take. And the types of clustering, there are several ways in which we can categorize the clustering algorithms. One major way, important way in which we characterize is whether we are creating a hierarchical clusters or partitional clusters. So when we are talking about a partitional cluster, what we are saying is that we are dividing all the data objects that we have into non-overlapping subsets, such that every data object will belong to only one subset. So in that case, what we have got is a clear partition. So it is like you cannot have so it is like states in a country. So you cannot say that there is a clear-cut demarcation and one state ends here and another state starts there. So in such cases, it does, so there are several situations where we want to have a partitional cluster. But there will be several situations where we may also like a hierarchical clustering. So here we are organizing the data into a hierarchy, and thereby we are clustering. So many times what we see is that, let's say we are looking at the taxonomy of the living creatures. So we know that there are many, we can always create them into broad categories, 2 broad categories, maybe animals and birds. But there can be many hierarchies among those categories. So if you look at a partitional cluster, it will somewhat come like this. If you have these as original points, and we are going to get a partitional clustering where each point belongs to one of these clusters, and we have created 3 such clusters. And if we are considering the hierarchical cluster, they will look somewhat like this. So here there is a clear-cut hierarchy. So we have this one, and then 2 is a part of 1, and then 3 is part of 2. So this is the way we have done it, and as you can see, this is represented using the hierarchical clustering can be represented using a dendrogram. This is a graph which is showing the mergers of the points into a cluster. So it is showing that P2 and P3 joined into a cluster, and then the next level is that P4 joined with them to create a next level, and so on. Or we can create a hierarchical cluster of different forms. So the P1 and P2 belong to one, and P3, P4, and then they are joined together at a higher level. And we may have several other ways to characterize a clustering. So one can be that exclusive and non-exclusive. So in a non-exclusive clustering, a point may belong to multiple clusters. So that is to say, when we can create a probability of belonging, a kind of a fuzzy clusters where a point may belong to both the clusters with the different weighties. So that can be one, and then the thing is, we can also have a partial and complete. So where we are thinking in terms of creating a clustering only for some of the points, not for all of that. And then we may even have a heterogeneous and homogeneous. So that is based on the kind of shapes and the densities that we are doing. For example, there may be points with the diverse densities if you are looking at a data that is spread over a two-dimensional space. So we may consider creating some heterogeneous clusters where the density can be lower and some where the density is higher. And the clusters can also be categorized by the separation, that is, some of them which are well separated, and some are center based, and some are based on contiguity, and some are based on the density. So if we look at this picture here, what we are seeing is here we got three well separated clusters. And if we are going with a center based clusters, so what we can see is that the separation between these two is very low, and we are talking about red and blue, and similarly the separation between green and yellow is also low. But using a criteria of a center and trying to build a cluster around that, then we are going to get the four center based clusters here. And we may go with a clustering which is a contiguity based. So we are constantly finding the shape which expands based on the density of the points that are available within that. And we are keen that it should be contiguous. So in such case, we may be getting the clusters of this form. For example, you can see here it created one cluster here and another cluster of this one. Though we can see that the distance between these 2 points is closer compared to the distance between these 2 points. So if you're looking at point 1, point 2 and point 3, you can see that the point 2, point 3 belong to one cluster, and point 1 and point 1 belongs to a different cluster. Though we can see that the distance between 1 and 2 is closer compared to the distance between 2 and 3. So we can also create density based clusters. So we have to constantly keep looking for the density of the points that are there in the neighborhood, and thereby we can create a cluster. Or we can create some conceptual clusters which are representing a particular concept. And many times we want to understand a cluster through an objective function. So whenever we create a cluster, we do have a clear-cut objective for which we want to do, and then we may be able to express that using an objective function. Then if we want to look at we want to divide all the data points that we have into various forms of cluster, and we want to find out the one which gives the best objective function, it's going to be a very, very complex problem. So we may have to go for one particular global or local objective, and we may just try to maximize as per within the constraints of the algorithm, rather than try to find an exhaustive evaluation of all possibilities. So when we are looking at the hierarchical clustering, and they generally go with a local objective, so that is at some point they say that there is the breakdown is no longer feasible or useful. So initially we have 100 points, we divided them into two sets of 50 or 50 points and 50 points, and again one of those 50 points we divided into 30 and 20. And there we realized that it doesn't make sense to do a further division. So we have reached some local objectives and we stopped. And when we are looking at a partitional algorithms, we may go with a particular global objective that we have and proceed. And added to that, we may have a parameterized models to represent those objectives that we have. And sometimes we may want to solve the problem using through some mapping approaches. For example, we may have many points within our universe or our space, and then we are trying to look at the proximity matrix between each point, and we are using some weightage also to look at the calculate the proximity. So here what we are trying to do is that we have converted this into a problem of graph where each edge has a weightage, and then we are doing a clustering by breaking the graph along the components based on the weightage. So wherever we see that the proximity is the least, we are breaking that line or the edge. So this is one way in which we can conceive of it. And some of the important characteristics that play a role when we are doing a cluster analysis is the way we use the proximity density measure with the data, and the type of the attribute, and the data itself may have some correlation between it, and the dimensionality, noise, outliers, distribution. All these points are going to play a significant role.